Welcome to section 4.7. We are talking about the concept of optimization. So throughout this chapter, we have looked at the idea of determining maximum and minimum values, both local and absolute. In this section, we're looking at some mathematical modeling involving this process. So we're going to look at some problems in context and see how we can apply this process of max and min to alternative types of questions rather than just find the max or min straight up. So when we're setting up an optimization problem, the flow of the problems is going to be very similar from problem to problem. What's going to change are the scenarios, the specific numbers, the formula specifically that we're going to use from question to question will be different, but the overall process should remain about the same. So when we're solving an optimization problem, we want to, of course, read the question carefully, make sure that you understand what the question is asking you for, use that to draw a diagram when applicable. If there is a scenario that offers an opportunity to draw a picture of it, that's never a bad idea to help yourself visualize it. That can help kind of spark ideas. We need to assign variables. So we take all of the known and unknown values and establish letters to them. We want to express the quantity that we want to maximize or minimize in terms of the other variables. So we're going to figure out, again, what the question is asking us to maximize or minimize, and then write that in a formula of some sort. If this expression contains more than one variable, eliminate all but one of them. So all of this is really just kind of set up, and then we get to the part where it says find the absolute max or min value. Okay, so all of the calculus stuff that we're doing all falls here in step 6. So let's go ahead and dive right into this and take a look at an example. So a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so we have 2,400 feet of fencing, a rectangular field that borders a river. So let's go ahead and put the rectangular field, and then there's going to be a river on this side. Okay, so that's the completion of the rectangle there. So what are we trying to maximize or minimize here? We want the dimensions of the field that has the largest area. So this expression right here, this is what tells us we're trying to maximize area. So the area of this rectangle. Now we need to go ahead and establish some variables for these side lengths here. So we'll just call this side X and this side Y. You can call them whatever you like. But we're trying to maximize area. So if we establish our formula, area of a rectangle is just width times length. So just X times Y. So we've established our variables, we have our formula, but this formula is in terms of two variables. So we need to go ahead and get rid of one of them. So we're going to relate X and Y using the one other piece of information that we have, that the farmer has 2,400 feet of fencing. So the fencing, that's this orange section right here. So basically, the sum of all of these pieces should add up to 2,400, because that's how much fencing he has. So there's going to be two X's and one Y that add up to 2,400 feet of fencing. And notice we have a y, single y right here. I'm going to go ahead and subtract the 2x to the other side. That leaves us with y equals 2400 minus 2x. And now this can go into this formula for the area. So we're going to get area in terms of x only. That's going to be x times 2400 minus 2x. So let's go ahead and multiply that out. So that's going to be 2400x minus 2x squared. And now we've gotten to our calculus step. So we expressed the quantity in terms of other variables. We eliminated all but one of them. Now we need to find the max or min value. So we can go about this process. Now let's take the derivative. So we're going to get a prime of x is 2400 minus 4x. We're going to set that equal to 0. So we get 4x equals 2400. So x is 600. Now, does this actually produce a maximum value? Let's just verify. So verify that it's a maximum. So we can just do the first derivative test here. So we'll just put 600 on a number line, and we'll choose one value to the left of it, even just 0, and you'll see you get positive 2400, so that's positive. Choose a number bigger than it, so like 1000, and then you get 2400 minus 4000, so that would be a negative. So we see that the function is going from increasing to decreasing. So it is a maximum. And we need the dimensions. So we have x, we need y, but we know what y is in terms of x. So let's go ahead. Y equals 2400 minus 2 times 600. So that's 1200. So here we have our two values. And as with any of these problems in context, you need to give an answer that is in context. So we can say the dimensions of the field that maximize area are 600 feet by 1200 feet. And again, it is important at the end of the problem just to check back really quick and make sure that you did actually answer the question. Because we were trying to maximize the area, but it didn't ask us what the area was. That's a simple enough calculation. You just multiply these two together. But like if we gave this answer and the question said, what is the largest area? Then technically our answer would be wrong because we didn't answer with the area. Or vice versa, right? If we just multiplied them together and wrote the area here instead of this, then that would have been incorrect. So you just have to double check, make sure that the answer that you're giving is actually what the question asked for. Now, we in this process are trying to find absolute max and min values for these functions. And the process we went through just involved finding a local maximum. But the nice thing about these types of problems, and there's this little blurb down here at the bottom, if we suppose that C is the only critical point of a continuous function on an interval, so C is the only critical point of a continuous function. If C is a local maximum, it is the absolute maximum. And if C is a local minimum, it is the absolute minimum. So in other words, if you only have one critical point and it's a max, it has to be the absolute max. And if you have a critical point that's a min, it has to be the absolute min. Because if you think about what this function is doing, it starts off down here, it grows up to this point, and then goes back down again. There's no way for the value to go back up above this if that's the only critical point, right? The other critical point would have to make it turn back like this, but we don't have another critical point. So as long as it's the only critical point for the function and the function is continuous, then we may conclude that it's an absolute without actually having to do the work of finding an absolute extrema. Let's take a look at this next example here. So a little bit different. Find the point on the parabola y squared equals 2x that is closest to the point 1, 4. So as you can see, I have kind of the diagram over here. So we have the sideways opening parabola, we have the point 1, 4. We're trying to find the point on this parabola that is the closest to the point 1, 4. Now, in terms of a max or min problem here, we need to figure out what we're trying to optimize. So find the point on the parabola that is closest to this point. When we say closest to, that's the key terminology here. When we say that it is closest to the point 1, 4, what we're really talking about is the distance, right? The distance between this point and this graph. And when it's closest, that's the smallest distance. So distance is minimized. So we would start off by using the distance formula between this point and this graph, or some unknown point on this graph. And I'm going to put it up here just because this problem does take up a bit of space. So distance, we have d equals the square root of x minus 1 squared, that's the 1 from this point, plus y minus 4 squared, again from that point. So this would be our formula in terms of x and y. Now, we don't want it in terms of x and y. We want it in terms of one or the other. So we can go ahead and use this formula now, right? Because this would just be any point, right? That would be any point around here. We don't want just any point. We want a point that specifically follows this relationship. So we can use that to actually eliminate one of the variables. I don't really want another square root in here, so I'm going to go ahead and solve for the x. So this would give us x equals 1/2 y squared. And then we're going to go ahead and put that in there. So distance, that's 1/2 y squared minus 1 squared plus y minus 4 squared. Now, here comes the part that I'm going to change this up a little bit. So try to follow kind of my logic here as we go. This, as a formula, this is perfectly fine. We could work with this formula, take its derivative, and then try to minimize and find the values that minimize this formula. However, having this expression for y's inside of a radical is not ideal. It makes the process a lot harder. So I want to take note. So note any values that minimize D would also minimize D squared. So any numbers for x and y that would make this formula minimized, if we were to square both sides of this and get D squared, that would get rid of the square root. Any numbers that minimize the original would also minimize the D squared, right? So any numbers that minimize D would also be minimums for D squared. We can use this fact to our advantage because then we can use D squared as our function instead. Because it's simpler. So, and I will reiterate, it's not wrong to use this original version of the formula, but it's going to be a lot simpler to use D squared. So this will be what we call f of y. So that's 1/2 y squared minus 1 squared plus y minus 4 squared. So this is the formula that we're going to minimize. So we can now work with this function instead, but the values we get out of it will be the same minimum values that we would get for the original. Okay, so let's go ahead and now apply our process. So we're going to get f prime. So we need to use a little bit of chain rule on this. So we're going to bring down the 2. 1/2 y squared minus 1 times derivative of the inside. So bring down the 2. So that's just y plus 2 times y minus 4. So let's see what we get here. So this is just y squared minus 2 and then times y. So that's y cubed minus 2y plus 2y minus 8. So we have y cubed minus 8, and we're going to set that equal to 0. So we get y cubed equals 8, so y is 2. Right, and then when y is 2, that means x, if you remember, x is 1/2 y squared, so x is 1/2 2 squared, so 1/2 of 4, which is also 2. We can verify that it's a maximum. Just put 2 right there. Check that in f prime. Check something around it. So like if we took 0, we would get -2. Actually, no, we would get 0. We would just get -4. So that would be... wait a second. If we took 0... oh yeah, no, that's right. Sorry, I had in my head that we were looking for a maximum. We're looking for a minimum. Yeah, so that's right. So if you took 0, right, it would just give us -8. So that's a negative. If we took something like 3, that would give us a positive and a negative. Let's see. So we get 27. Those cancel. Minus 8. 27 minus 8 is 19. So that's a positive. So we're going down and then up. So it is a minimum, and it's the only critical point on this entire function, which means that it has to be the absolute. So we can say the closest point on y squared equals 2x to the point 1, 4 is the point 2, 2. And you can see if we look at the graph here on Desmos, so I've got it pulled up right here. So like when a is 2, you have this point in question. So this is the shortest distance. If we let it kind of move around like this, you can see if we stop it at any moment in time, the distance, the length of this purple line is going to be longer at any one of these points. So even like even that close, 2.35, it's still slightly longer than it is at 2. So all of these distances, and that is the shortest distance that this function can take on. All right. Let's take a look at one more. A man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. The point C is directly across the river from A, and the point D is the point between B and C where he lands. If he can row at 6 kilometers per hour and run at 8 kilometers per hour, where should he land to reach B as soon as possible? Okay, so we've got 2 sides of a river. He's standing at point A on the left-hand side of the river, and he's trying to get to point B down here. So let's see what we know here. We know the river is 3 kilometers wide, so we know this distance is 3. We know the distance downstream is 8 kilometers from A to B, so that would be this distance would be 8. So let's go ahead and put a point there. So just straight across. So the distance from B to C would be 8. Okay. And then the point D is the point between B and C where he lands. So he could go, straight across and then just run the whole way, or he could row all the way straight to point B, or he could go somewhere in between. So that somewhere in between, that right there, that's our point D. That's our somewhere in between. So we need to establish some variables here, because we know the total distance across is 3, we know the total distance down is 8, but we don't know how much of it he rode and how much of it he ran. So let's go ahead and establish, I'm going to let this be x in here. That's the distance between C and D. So we're going to let x be the distance from C to D. So that means x has to be between 0 and 8. Right? Because if he lands at C, then that's 0. If he lands at B, then that's 8. and then anywhere in between there. So what are we looking for? It says, where should he land? So how far? So we're looking for the value of x to reach b as soon as possible. So where should he land to reach b as soon as possible? So this is asking us to find x. And when we say as soon as possible, we're trying to minimize time. We're trying to minimize the time that it takes for the man to get there. So we need to set up a formula that's somehow going to relate the distance that he's traveling with the amount of time that it takes to get there. And we also know his rates, right? We know that he rows at 6 and runs at 8. And so we do have a formula for that. And that is the formula distance equals rate times time. You might remember it from algebra. And we're looking for the time. So I'm going to go ahead and divide the r over there. So time is distance over rate. So the amount of time that it's going to take, well, he's going to spend some of the time rowing and some of the time running. And the rates are different, so we need to go ahead and split those into separate cases. So we're going to have the rowing distance over rowing rate plus the running distance over the running rate and we can figure out, we know the rates right off. The distance will be written in terms of x. So we're going to get t of x. The rowing distance, that's going to be this length right here. So if we have, that's A and that's C. We have this right triangle here. So this is our rowing distance. So I'll call it y if you like. But that's x, and we know this is the length of the river, that's 3. So to find this side, we would use the Pythagorean theorem, right? So y squared equals x squared plus 3 squared. So y is the square root of x squared plus 9. So we'll go ahead and put that in here. So that's going to be square root of x squared plus 9 over his rowing rate, which is 6. Then distance running. So the distance running is not x here. It's whatever is left. So it's this distance. So it's not x. It's actually the 8 minus the x. So it's going to be 8 minus x over the running rate, which is 8. And now, so this problem obviously much more heavily involved with the setup. But now we can apply our calculus techniques. So we'll go ahead and take t prime. So we're going to take the derivative of the square root. The 1/6 is just going to tag along. But that would be 1 over 6 times 2 root x squared plus 9 times the derivative of x squared plus 9, which is 2x. plus derivative of 8 minus x over 8 is just negative 1 over 8. So we get just x over 6 rad x squared plus 9 minus 1/8. We'll set that equal to 0. If we go through this process, so I won't do all of this, but x over 6 rad x squared plus 9 equals 1/8. Cross multiply, square both sides, solve everything out. We end up getting x is 9 over radical 7. And if we verify that value, pick something less than that for the derivative, so like 0, we end up getting negative 1/8. Pick something greater than that number, so that's like 9 over something between 2 and 3. So we'll pick like 5, for example. So we get 5 over 6 times rad 34. Check that against the 1/8. You'll find that it does do this. So it does give us a minimum for that time formula. Now, we got the x value. Let's double check and make sure what we're actually looking for. So where should he land to reach B as soon as possible? So we are looking for the x value. The x value is the answer. So we'll go ahead and give the exact answer, and we'll put in the approximation as well. So we'll say the man should land the boat at a point 9 over rad 7, which again is approximately 3.4 kilometers downstream. To get there as quickly as possible. All right, so we've seen 3 very different looking problems today in this section, but problems that despite differences in setup, differences in like formulas, differences in numbers, all revolve around this same process. So the idea of reading the question carefully, drawing a diagram if possible, establishing variables, setting up a formula, and then differentiating the formula to find maxes and mins. That is the process of optimization. And that brings us to the end of section 4.7.